We begin with a simple quadratic function, x minus 2 squared. We'll be graphing this in the Cartesian coordinate plane from -10 to 10 in both directions. To begin with, we consider the untransformed quadratic parent function, f of x is equal to x squared, and three key feature points, -1, 1, 0, 0, and 1, 1. In our example, with f of x equal x minus 2 squared, we shift everything to the right by 2 units. This means we take each of the x values and add 2 to them. Finally, we should also include any intercepts, both x and y, which we can find. In this example, by substituting 0 for x, we find that the y value is 4. This is our final sketch of the graph f of x is equal to x minus 2 squared. In our next example, we'll be looking at f of x is equal to -x squared plus 3. First of all, the negative in front of the x squared indicates a reflection over the x-axis. Here I have sketched both the function that we are graphing and g of x is equal to -x squared. There were 2 points that were unlabeled where the function crossed the x-axis. We can solve for these points by setting the function equal to 0 and then solving for x. Here then is the complete sketch of our graph, including the x-intercepts. In our final example, we take into account all possible combinations of transformations on the standard form of a quadratic function. Note, there is a vertical stretch by a factor of 2, as well as 2 shifts, both right 3 and down 1. A very useful tactic is to take the 3 original points, -1, 1, 0, 0, and 1, 1, and apply the transformations. A vertical stretch by a factor of 2 would be to multiply the y value by 2. From there, we would shift this right 3 and down 1, landing us with a vertex at 3, -1. We repeat these for each of the 3 feature points. In this case, 1, 1 first gets mapped to 1, 2 before being shifted over to 4, 1. In a similar way, -1, 1 is mapped to -1, 2, and from -1, 2 into 2, 1. Note that the order of operations here is in fact very important. A vertical stretch is a multiplication, whereas the shifts are both addition and subtraction. By plotting these 3 points, we gain enough information to be able to sketch the graph. Here I have superimposed both the untransformed and the transformed function. Notice that once again there are 2 x-intercepts which we will need to solve for to complete our sketch. We do this by setting the f of x equal to 0 and then solving for x. Note, we should find 2 solutions. Add 1 to both sides of the equation, divide by 2, take the square root of both sides. Do not forget to include a plus minus on the outside of your square root. Finally, we add 3 to both sides, and here I've also rationalized the square root of 1/2 into the proper square root of 2 over 2. Here you can see a portion of the graph where I've zoomed in on the x-intercepts. Notice that both the intercepts occur square root of 2 over 2 away from the vertex value of 3. Here's the complete sketch of the function. Let's compare our most recent sketch to a calculator-generated answer. Enter the function into your calculator and follow along. First, note that the standard zoom looks very similar to our final sketch. Let's go ahead and zoom in on the region where the x-intercepts occur. Once we are here, we can actually calculate the x-intercept values. Open up the Calculate menu by pressing second trace, and then either press 2 or scroll down to select number 2, which says 0. This stands for the 0 of a function, which is where the y values are 0. Just as with finding a minimum or maximum, we must set a left and right bound around the 0. Here I am finding the leftmost 0 by setting the left bound above the 0 to the left and setting the right bound below the 0 to the right. As per usual, the calculator will ask for us to guess, and you are welcome to move the cursor closer to the 0, but as long as you have set good left and right bounds, it will not matter where you press enter. Here we see that the calculator has given the 0 of 2.928932. This seems to be different from the 0 which we calculated earlier. Let's verify. Go back to your main screen by pressing second mode, which will quit the graphing screen. type in the 0 which we found for the left 0. As a reminder, that was 3 minus the square root of 2 over 2. If you press enter, you will find the same decimal digits that we saw on the graph. Here is one of the many shortcomings of a calculator. When finding the 0, it can only give a decimal representation of an answer which you ought to be able to find analytically and exactly. Do note that if I ever ask you to find a 0, I will expect to see the full 3 minus the square root of 2 over 2, not the decimal answer 2.92, etc.